Hello friends, welcome to PansimTech Private Limited. So today we are going to just see about the derivations of different governing equations. So we'll start with continuity, and in your subsequent lecture you will get momentum equations, energy equations, derivations also. So this will be complete series you will get free of cost. So you can enjoy this lecture, and it will be very informative. So before dive down into the lecture, so let's understand little bit brief about PansimTech Private Limited. So we are engineering consulting service provider, and we have different domain expertise. We are already connected with some various industries, and like we are doing CFD simulations for particular industries, FEA, thermal simulations, product development, CAD CAM, verification and validation, virtual prototyping, etc. We are also giving corporate and academic training, as well as we are also supplying people out. We are also doing people outsourcing to different industries, as well as mentorship also. So you'll you can contact us. We have detailed website, and we are also incubated of IIST Sipur. So Sipur is something central government college, engineering college. It's very old college in Kolkata. So our technical headquarter it is in Kolkata, and business operations we are doing from NCR, Delhi, and Kolkata. So without wasting our time, let's understand what are the different deep down in continuity equation. So coming to the next slide. So these are the different governing equations: continuity, momentum, energy. So today we are going to see about continuity equation. In subsequent lecture, we'll understand what is momentum equation, energy equations. So today we'll see what are the different derivations related to continuity equations. Okay. Before going to the derivations of continuity equations, there are some terms that we need to understand. So what are the different modeling of the flow that we need to understand? So what is FCV? Fixed control volume. So there are basically in any conservation equations, you can see two terms: conservation form and non-conservation form. So what is conservation form? If it is fixed in, if suppose your element or control volume, it is fixed in space and it's not moving, then we can say this is in conservative form. And if it is moving along with the fluid, like you can see here from the picture, so that we can say, okay, it's in conservation form. So generally equations we can see in both form, but generally we are preferring for conservation form. Why? Because we can see, suppose one body is standing and flow is moving, like wind tunnel test. What exactly wind tunnel test we are doing? We are not rotating the whole car within the tunnel. We are simply putting the car stationary and moving the fluid with relative velocity approach we are doing. So that is why we are doing with conservative form. Okay, substantial derivative we have to understand little bit. So what is basically substantial derivative is that, suppose if you want to see the v, so this is the equation of velocity vector v, where u, v, w is local velocity in x, y, z component, and with respect to different time coordinates and space coordinates. So if you'll see our next slide, then we'll come to, so here you can see from position 1 to position 2, one fluid element is moving at a particular time from time interval t1 to t2. So please consider this for this moment. We'll understand more in the detailed slide in the next. So if suppose this is point 1, so density is changing at particular point 1 with respect to x1, y1 and z1 and t1. So if it is moving from 1 to 2, so this is the locus of the fluid element. So what if we are suppose using uh, mathematical modeling, that is Taylor series? Why we are choosing Taylor? There are other series as also Newton-Raphson method, etc., etc. But Taylor series we are choosing because of two things. From the beginning, evolution of the CFD or maybe numerical schemes, we are using this Taylor series in different schemes like finite difference method. We are generally using this Taylor series because it is very simple to use. So if suppose if we are saying, if we are taking at position 2, what is the change in velocity at position 2? So we have to take at position 1 first, then change in density with respect to position 1 at each locus. Okay, so here you can see. So in terms of partial derivation, what we can say rho 2 at point 2 equal to initial value plus change in with respect to x into del x, change in with respect to y of 1 means for one element 1. So with respect to y into delta y, change in rho means density with respect to z at for position 1 for with into del z. So if you are cancelling these two term, it will again become density. Just trying to correlate the units. So here also kg per meter, here also kg per meter, something like that. So if you are taking common of T2 minus T1, or maybe you can divide it from T2 minus T1. So what will become? So this will be something nothing but dou rho by dou T, and here it is what? Dou rho by dou x into dou x by dou T. Dou x by dou T is what? Your U. So similarly here dou rho by dou y, it is nothing but V. Here it is what? Dou rho by dou z, it is nothing but W. So basically these plus dou rho by dou 2. So dou rho by dt. So that means can we call this term as u? Changing velocity in x direction with respect to time is what? Sorry, changing distance with respect to time is what? Velocity. Velocity in x direction. So you can say u. See next slide. So basically that thing I was calling. So what exactly it is? Change in velocity with respect to time in x direction is u, v and w. V means y direction v and z means w. So if you substitute all those equations, you will get this equation. And if suppose you are substituting this parameter del, so del is nothing but in terms of vector calculus in mathematics, we calling it I into dou rho by dou x, z into dou rho by dou y, k dou rho by dou z. If you are considering del square, that is I dou square by dou x square, j dou square by dou y square, dou square by dou z square into k. So that means this we call as del square. But here I am talking about only del. Dou square is your Laplace term that we can see in Navier-Stokes equation, not here. So here we are just considering only del. So if you will substitute this del into this, what you will get? It will get something like this. So this is your continuity. Yes, basically not continuous. Sorry, this is your derivative term for any parameter. If you are considering density is the parameter, so change in density with respect to local velocity. So this is your what? This is your local term that we for a steady state this will become 0, and this is your convective term. So you can see from here convective term and local term. So I can give you one example. Suppose a girl is standing on a window, and one suppose one guy is just doing some music of piano. He is going from that. So if girl is seeing from that portion, so that means when the person is going from uh, the point where it is crossing the girl, that total distance from that initial to final is your convective term, but the point from where it is crossing to the girl, that means that is the local term. Girl is seeing locally with respect to time, that is your dt. So but if we are not considering, that means for a steady state simulation, dou rho by dou t equal to 0. Coming to the next. Now this is not important. So now if I am coming to the continue, actually now coming to the continuity equations derivation. So what you are seeing here, this is one element size, okay, control volume size. The length of the control volume is dou in x direction it is delta dx, and y direction dy, z direction dz. So if u component, what you can see, u is xyz t, v is xyz t. So that means it is in x direction, it is in y direction, it is in z direction, u, v and w. Now you can see from here. So if you will see, the rho into u is what? Area into velocity, that is your mass flow rate. Sorry, area into velocity is what? Dou y by dou z is your area for this phase. That means if we are considering in x direction, so this is your x direction. So what is the area? This is the area. Let me take pen. So for x direction, this is one area and this is one another area. So what is the term here? You are saying this is your final term. That means flow coming out and flow going in. So what is the flow accumulation? This minus this, correct? That you can see it from here. So what is this basically? Let me make you a little bit more understanding in this. So this is what? Rho into velocity into area, if you're multiplying it here. So rho into area into velocity is what? First of all, area into velocity was volume flow rate. Multiply by rho is what? Mass flow rate. So that means rho into area into velocity is what? It is mass flow rate. Okay. So change in mass flow rate for this position is will be what? Initial mass flow rate plus change in mass flow rate with respect to x direction. That means if you are calling this as a x, so that will be x. So that means see it here with respect to x, this will be x. So change in velocity with respect to x into del x, this is your x direction. Final mass flow rate, initial mass flow rate going in. So out minus in is your total mass flow rate in x direction. Similarly for y direction, so this will be your y direction, this will be your y direction, and so that means if you will go through the y, it will become what? It will become del y. So here you can see change in mass flow rate in y direction multiply by dy. Okay, so this is your and similarly in z direction, this will be something like this. So what is the net mass flow rate? The net mass flow rate will be summation of these three, 1, 2 and 3. So this will be your net mass flow rate. And what is the accumulated mass flow rate? This will be the accumulated mass flow rate. That means rate of increase of mass. So as per mass flow rate, if this should be equal to this, that means if we are cancelling this out, so and taking this left hand side, right hand side towards left hand side, it will become something like this. And in terms of partial derivation, so this is your final equation. So this is all about continuity equation for Cartesian coordinate. We have other two, radial and cylindrical, but generally that will become in the beginning stage, it will become too complex. So let's understand with Cartesian coordinates. So it is easy to understand. So this is all about our Cartesian mass flow rate derivation, sorry, continuity equation derivation. In our next class, we are going to see momentum and how Navier-Stokes equation is derived from the momentum, that also we will see. And later on in the subsequent lecture, we will see derivation of energy equations. Why this derivation I am showing you? Because this derivation is required to understand the basics, because after on, once you will understand the software, like any software, they are nothing doing, they are simply discretizing these governing equations into algebraic form and putting into the software. Okay, we'll see it later. Okay, okay, so this is all about, so this is our corporate and academic training program. We are also doing R&D projects. So if you have any, if you are interested in corporate training program or academic program, please join us and we'll provide certificates also. And there are some different labels. Based on the labels you will get, it's totally up to your choice. So that is why. So let's see our next lecture. It will be more informative, and please subscribe our channel and press the bell icon so that you will get the notification. Thank you very much. For anything you can contact us on this website, also on this email, phone number, you can call us. Okay, thank you very much. Thank you very much.